A person throws a ball straight up with an initial velocity of 50 meters per second and then catches it when it returns back. What is the maximum height reached by the ball? What is the time taken for reaching the maximum height? What is the time taken for the whole journey? What is the final velocity when the ball returns back? Ignore air and other resistances. What is happening here?
The stone is traveling upwards, so it is not under free fall acceleration. How can I solve such problems?
The expression, freely falling, does not necessarily mean an object is falling down. A freely falling object is any object moving either upward or downward under the influence of gravity alone. In such scenarios, the only acceleration acting upon the object is Earth's gravity, which is constant. Therefore, we can use our constant acceleration equations for an object thrown up and for an object falling down. The only criteria is that the object should be under the influence of gravity alone.
Okay, I got that. Let me write the equation for solving this problem.
Do not start with the equation. First, draw the diagram explaining the situation.
Okay. The body is thrown up vertically, so the initial velocity of the body is directed upwards. The body is under the influence of gravity alone, and gravity is always directed down towards the center of Earth, that is downwards. So velocity and acceleration are in opposite direction during the upward journey.
That's correct. Under these circumstances, the velocity of the object gradually decreases, and it becomes zero momentarily at the highest point.
Okay. So if I need to calculate the highest point reached by the body thrown up, I need to use this fact that the velocity at the highest point would be zero.
That's correct. Implicit data is important. The phrase, "How high does the object go?" refers to the maximum height which occurs when the final velocity in the vertical direction is zero. Also, an object dropped freely implies that the initial velocity of the object is zero.
Okay.
Coming back to the problem, try explaining what happens to the object next.
Okay. Even though the velocity is zero at the highest point, the body will still be under the influence of gravity, and hence acceleration is not zero at the top. Throughout the journey of the object, acceleration due to gravity is always directed downwards.
Very good analysis.
So if I draw a diagram explaining the situation, it would be as follows. We can see that during the upward journey, velocity and acceleration are in opposite direction, and during downward journey, both of them are in same direction. I will consider upward journey first, and I will take upward direction as positive. So during upward journey, I have the following data. Initial velocity v0 equals plus 50 meters per second. Final velocity v equals 0 meters per second. Acceleration equals minus 9.8 meters per second square. Since I have taken upward direction as positive and acceleration due to gravity is pointing in downward direction, I need to calculate displacement. Since I know the initial velocity, final velocity, and acceleration, I will use the equation v square minus v0 square is equal to 2 into a into y minus y0. Substituting the values and solving for displacement, I get 0 square minus 50 square equals 2 into minus 9.8 into y minus y0. Canceling the units and solving for displacement, I get displacement y minus y naught equals 127.55 meters. I will solve the next question. What is the time taken for reaching the maximum height? Using the equation v equals v naught plus a into t, I get 0 equals 50 plus minus 9.8 into t. Therefore t equals 5.1 seconds. I will solve the next question. What is the time taken for the whole journey? Now I will calculate the time taken during downward journey. If I add the time taken for upward journey and the time taken for downward journey, I get the total time taken for the journey. During the downward motion, I have following data. Initial velocity v naught equals 0 meters per second, acceleration a equals plus 9.8 meters per second square. I need to calculate time. Also, I know that the displacement during downward motion is same as the displacement during upward motion. Therefore displacement y minus y naught equals 127.55 meters. I use the equation y minus y naught equals v naught into t plus at squared divided by 2. Substituting the values, I get 127.55 equals 0 into t plus 9.8 into t squared divided by 2. Therefore t equals 5.1 seconds. This looks familiar. This is the same time it took for the body to reach the maximum height.
That is correct. I need to explain you an important point here. The motion of an object that is thrown up and eventually returns to Earth has a symmetry that is useful to keep in mind from the point of view of problem solving. There exists time symmetry and velocity symmetry in a free fall. The time required by the object to reach maximum height equals the time required by the object to return to its starting point.
Okay.
A type of symmetry involving speed also exists. If you consider any displacement y above the point of release, the object's speed during the upward trip equals the speed during the downward trip. For example, calculate the velocity when the displacement is equal to 10 meters.
Okay. Since I know the initial velocity, displacement, and acceleration, I will use the equation v square minus v naught square is equal to 2 into a into y minus y naught. Substituting the values, I get v square minus v naught square is equal to 2 into minus 9.8 into 10.
Note here that if you had not taken into consideration the direction and signs, you might have used plus 9.8 meters per second square for acceleration, which gives you wrong answer. You will find that instead of decreasing, the velocity increases as the object moves upwards,
which implies v is equal to square root of 2304. Therefore v is equal to plus or minus 48 meters per second.
As you can see, there are two values of velocity when the displacement is equal to 10 meters. One instance of plus 48 meters per second is when the ball is traveling upwards. Another instance of minus 48 meters per second is when the ball is traveling downwards. In both these cases, when the ball travels a displacement of 10 meters, the speed, that is magnitude of velocity, is equal in both the directions. Likewise, magnitude of velocity when the ball returns to its point of release equals its initial velocity, that is 50 meters per second, but the direction is reversed, it is now directed downwards. Can you explain why this symmetry arises?
Yes. I see the reason behind it. Remembering the concept of acceleration, as the ball travels upwards, it loses 9.8 meters per second in speed each second. Then during the downward journey, it gains back the same amount of speed each second.
Can you explain this, taking an example?
Yes. I will take an example wherein a ball is thrown up with an initial velocity of 49 meters per second. I choose upward direction as positive and downward direction as negative. The body undergoes an acceleration of minus 9.8 meters per second square during its upward journey, which means after each second, the change in the velocity should equal 9.8 meters per second. Using the equation, v is equal to v naught plus a into t, I get velocity after 1 second is equal to 49 plus minus 9.8 into 1, which equals 39.2. In other words, the body loses 9.8 meters per second for every second during its upward journey. Continuing in the same way, velocity at the end of second equals 39.2 minus 9.8, which is equal to 29.4 meters per second, this same as 49 minus 2 into 9.8, using the formula v is equal to v naught plus a into t. Velocity at the end of third second is equal to 29.4 minus 9.8, which is equal to 19.6 meters per second. This same as 49 minus 3 into 9.8. Velocity at the end of fourth second is equal to 19.6 minus 9.8, which is equal to 9.8 meters per second. This same as 49 minus 4 into 9.8. Velocity at the end of fifth second is equal to 9.8 minus 9.8, which is equal to 0 meters per second. This same as 49 minus 5 into 9.8. After fifth second, the velocity of the ball becomes 0, which means it has reached its highest point. Therefore the ball starts to come down because of the gravity. During the downward motion, applying the same concept as above, the body undergoes an acceleration of plus 9.8 meters per second square, which means the velocity of the body increases by 9.8 meters per second every second. Velocity at the end of first second is equal to 0 plus 1 into minus 9.8, which equals minus 9.8 meters per second. Here acceleration due to gravity is negative since I considered upward motion as positive. Velocity at the end of second is equal to minus 9.8 plus minus 9.8, which is equal to minus 19.6 meters per second. This same as 0 plus 2 into minus 9.8. Velocity at the end of third second is equal to minus 19.6 plus minus 9.8, which is equal to minus 29.4 meters per second. This same as 0 plus 3 into minus 9.8. Velocity at the end of fourth second is equal to minus 29.4 plus minus 9.8 equals minus 39.2 meters per second. This same as 0 plus 4 into minus 9.8. Velocity at the end of fifth second is equal to minus 39.2 plus minus 9.8 equals minus 49 meters per second. This same as 0 plus 5 into minus 9.8. Note that if you had taken downward motion as positive, you would arrive at exactly the same results, but with opposite signs, as shown. We can see from this example that there exists a symmetry in speed and velocity. Proceeding with the problem, therefore the time taken for the whole journey equals 5.1 times 2 equals 10.2 seconds. The final velocity when the ball returns is same as the initial velocity, but opposite in direction. Therefore final velocity equals minus 50 meters per second.
That is correct.